ICPS workshop on irregularity. And this colloquium is also part of the ICPS IASC joint program. And I'm very glad to invite Professor Satya Prakash of Cardiff University to talk about gravitational astronomy. Incidentally, Satya is an alumnus of the League of Science, so it's a coming platform for Satya.
That's right, yeah. Yeah, thank you very much for inviting me. This is really a wonderful opportunity to come back to the home institution, especially because this is a joint colloquium. It makes it even bigger pleasure to give this talk. What I would like to do in this talk is to tell you about what gravitational waves are and what we can learn. I know there are quite a few experts in the audience, so you'll have to put up with me for telling you something trivial very frequently, but I hope there is something new for everyone towards the end of the lecture. The first 3 slides are the big picture really, and after that it's really detailed, so if you can stay awake for the first 3 slides, the beginners hopefully should get some idea of what gravitational waves are. So in Newton's theory of gravity, gravitation is described by a scalar field and it obeys Poisson equation, and there is no time delay between what the source does and the potential. There is absolutely no propagation effect incorporated because there are no time derivatives in this. It's not a wave equation, it's a Poisson equation, and therefore there are no gravitational waves in Einstein's theory, in Newton's theory of gravity, and it's a action at a distance theory. Whereas in Einstein's theory of gravity, gravitational field is first of all described by not a single scalar field but by a second rank tensor, G alpha beta, and when gravitational fields are very weak, you can decompose them into a background Minkowski metric eta alpha beta plus a small perturbation. So we would call that metric perturbation, and this may have magnitudes very, very tiny. So if you work out Einstein's equations in this approximation, when you can write the metric as a small perturbation over the Minkowski metric, then in a special gauge which is available in Einstein's theory of gravity, you can choose gauge degrees of freedom, then you can to choose a particular gauge in which Einstein's equations are linearized become very simple. They are wave equations for the metric perturbation, not quite the metric perturbation, but this trace reverse tensor, but nevertheless it is simply the same as giving you the distance between objects, so that's fine. So this quantity then obeys a wave equation with a source term. So if you have no source, then you can have solutions to this which are wave-like solutions, and the difference between these two is that whenever there is change in the distribution of matter, it is not felt immediately at the location of the field. There is a retardation, and that retardation is given by the coefficient of this d square by dt square, which is equal to, so it's the inverse of this, the coefficient sitting in front of this is the inverse of the square of speed at which the interaction propagates. In this case that's equal to 1. That means gravitational waves travel at the speed of light. There are other theories of gravity in which this may not be true, but we will be really focusing mostly on Einstein's theory of gravity. So in Einstein's theory then, gravitational waves are propagating ripples of space-time curvature, because once you are given the metric, you can construct the curvature tensor out of it, and that will be oscillatory if you have a field that is oscillating. So typically you get solutions that are oscillatory, that the non-stationary part, and that would be what we call gravitational waves. That will be the only slide that contains any equations in this talk, because it is meant to be a colloquium. Press the wrong button, it looks like. But then how are gravitational waves generated, and how can we detect them? What are the different frequency bands? I want to start with what we can observe with gravitational waves, because then it will tell us what detectors to consider to construct. So there are basically 4 quantities that we can observe, and inherent in them will be properties of sources which we can disentangle. The first in my list is luminosity of gravitational waves. We don't directly measure luminosity, but it's an important derivative of what we can observe. From what we can observe, we can conclude what the luminosity is, and that's a very strong function of aspherical velocity that is present in the system. So luminosity in gravitational waves produced by any astrophysical system is some asymmetry factor, which could be very tiny, like 10 to the minus 10 or 10 to the minus 20 or even 0, depending on how non-spherical the system is, multiplied by a very strong function of the speed in which is v by c to the power of 10. Typically, when we observe gravitational waves with a detector, the velocity might change by a factor of 4, and that will lead to luminosity increasing by a factor of 1,000,000. So as we observe a source through our detector, the source might brighten up 1,000,000 times, and that's a very spectacular change in luminosity, and that's the reason why some of the gravitational wave measurements that we can make are extremely accurate, because of this change, the variability that the system shows. But this luminosity is also can be expressed as an asymmetry factor, this similar asymmetry factor, multiplied by the source compactness. So here I have written it in a dimensionless form, m by r to the power of 5, where m is the typical mass in the system and r is typical size of the system, and it is m by r to the power of 5. So it's also a strong function of the source compactness. Typically these relationships hold good for gravitating systems, in which what I mean by that is the speed in the system is dictated by gravity. So if you have gravitating systems, then these two are identical relationships, and therefore it's not only a strong function of velocity, but it's also a strong function of compactness. And in order to have therefore very luminous objects, you must have very compact objects. It's no good having just very large velocities. You can produce relativistic, ultra relativistic velocities in particle colliders, but unless you can also make them very, very compact, you can't produce luminous gravitational waves. That's the point I would like to make there. Therefore, these two, both conditions hold good for very compact objects like neutron stars and black holes. For black holes, this ratio can approach unity, and this ratio also, of course, approaches unity. More importantly, for binary black holes, this asymmetry factor is close to 1. If you convert that asymmetry factor to a dimension-full quantity, here I have written luminosity in a dimensionless units, the factor that you need is c to the power of 5 divided by g. And this is 10 to the power of 52 joule per second. It's a tremendous luminosity. The luminosity is more than all the stars in all the universes, in all the, maybe not all the universes, but in all the galaxies in the universe. So the luminosity can exceed the luminosity in light of all the stars in the universe, maybe for only a brief period, milliseconds to seconds up to minutes, depending on the mass of the source, because it is the mass that determines the time scale. So that's about the luminosity. The amplitude of the radiation for most sources can be written as a product of two potentials. The d here is the distance to the source, and r here is the size of the source. M by d is the external potential of the source as I measure it for the source at the location of my detector. M by r is the internal gravitational potential of the source. So given objects at a given at a distance, 10 megaparsec, 100 megaparsec. All we have is this quantity which can be varied. Therefore, for most compact objects at a given distance, I have the greatest amplitude. So whether you look at the amplitude or luminosity, it turns out that gravitational wave sources will be best or strongest for the most compact objects. Therefore, gravitational wave detectors are essentially detectors of neutron stars and black holes. The frequency of the system very often is the dynamical frequency, namely the free fall time in the system. For binary systems, it is simply twice the orbital frequency typically, but that's only what is called the dominant frequency at which gravitational waves are emitted. You could also have some energy emitted in just the orbital frequency itself, 3 times the orbital frequency and so on, and immense amount of information is contained in these higher order modes, and that has been one of the important considerations in calculating waveforms very accurately, and the theme of this workshop actually focuses on computing waveforms. Getting the frequency and frequency evolution accurately is one of the goals of this workshops. So a binary of 20 solar masses, for instance, merges at 200 hertz. If you increase the mass by a factor of 10, that will decrease by a factor of 10. If you decrease the mass by a factor of 10, like 2 solar masses, which are appropriate for neutron stars, that will be 2000 hertz. Therefore, the range of masses from a few solar masses to few hundred solar masses are actually in the audio band, and very frequently we can actually listen to gravitational waves. If we had millions of graduate students, all we needed to do them was to give headphones and ask them to listen to that, and once in a while you will hear a chirp signal that was not arranged. I mean, you heard a bird chirping, but it will be a chirp signal amidst all the noise, and that's when we can say, hey, there is an interesting event. And that falls in the audio band, and that's makes it very convenient to convert these into audio files, etc. The fourth quantity that I'm interested in is the polarization. Gravitational waves in Einstein's theory of gravity have only 2 degrees of freedom, and there are 2 polarization states called plus and cross polarizations. In other theories of gravity, you can have other polarization modes, and that's one of the testing grounds. When we make gravitational wave observations, we can ask the question, how many different modes of polarizations are there? This is something that we cannot do with indirect observation of gravitational waves. For instance, Hulse-Taylor binary pulsar, which gives us a very strong evidence of the existence of gravitational waves. It is not direct observation because we cannot deduce what are the different polarization states of gravitational waves. So polarization is a very important property. It is going to play, hopefully, an important role in detecting stochastic gravitational wave backgrounds with electromagnetic radiation. So this goes on to, this slide is a summary of where our compact sources are going to be, what their frequencies are, and what are the instruments available to detect them. So this is a one slide summary of all the sources and the opportunities to detect those sources. So it's called the frequency mass diagram. The horizontal axis goes over 12 orders of magnitude, 1 solar mass all the way to 10 to the 12 solar masses, and the vertical axis gives you the frequency of these sources at various stages in the evolution. Systems could be at different points. So I have drawn a number of lines on this diagram to show you where the sources are expected to be. First, the forbidden region. There is a line here. As a function of mass, the frequency of the source seems to be decreasing. As you increase the mass, it is decreasing, and that is what is called the 4-4 quasi-normal mode. If you deform a black hole, then it gets rid of its deformity by emitting gravitational waves. These are called quasi-normal modes, and there are many different modes of radiation that are emitted These are the fundamental mode is called the 2-2. That is, these indices here are simply like the spherical harmonic indices. L equal to 2 is the dominant radiation, and M goes from minus L all the way to plus L. So the 2-2 mode is the dominant form of radiation, and that's given by this red line here. As you go to higher values of L, the frequency increases, but our experience is that once you go to something like L equal to 4, there is not much energy deposited in these higher order modes. Therefore, we don't expect deformed black holes to put a lot of energy into those higher order modes. Therefore, we don't really expect to see sources in this forbidden region, because that's the highest frequency into which black holes are probably putting in some energy. So that's the forbidden region, and that's again a testing ground for general relativity. If you see a 10 to the 6 solar mass object with something like 20 millihertz radiation, then that would be violating the prediction of general relativity. So that's the no radiation expected in that region. There are several other important lines here. This green dotted line, the dash dotted line, is what is called the law stable orbit frequency line. This line represents the transition of a binary from a state when it is inspiraling to a state when it is merging. Most of the energy is actually emitted in the region from very close to this law stable orbit frequency. So for instance, as the binary neutron star inspires, maybe that's not a good example. Let's take this intermediate mass binary black hole. As it evolves, the thick dotted line gives you the time to coalesce to be 3 years. So any binary that starts off on that line will take about 3 years. So this intermediate mass binary black hole might start off at something like 1 millihertz, and it will enter right into the band of ground-based detectors from space-based detectors and merge somewhere around a few tens of hertz depending on its mass. Whereas the supermassive black hole will take 3 years to merge, starting from a few times 10 to the minus 5 hertz, ending at 2 times 10 to the minus 3 hertz. So these are typical frequencies. 20 millihertz or 30 millihertz is the frequency at which it merges. That's the law stable orbit frequency. Now there is one other line here, or an area that has been marked out, which is called the chirp line. Although I don't say that on the diagram here, the region, any binary that starts off here, for instance, if this were to start off from here, the change in frequency in this system is less than 1 by 10 years. So if you observe the binary for 10 years, it will appear as though it is a continuous wave at a single frequency. If the frequency does not change, then you cannot really measure any of the parameters, which means you can't measure what the masses of the stars are, what are the component masses. You can't really get much physics out of systems that start out in this region of the parameter space, mass and radius, mass and frequency space. So this is, for me, I mean, you can observe them, you can detect them, but you can't really do much astrophysics or astronomy with them, and that's why I have marked out that region of the parameter space as well. So the regions, the 3 regions that I have marked out, in addition to various other shaded areas, are this blue region called the audio band. That's the region in which ground-based detectors are able to observe sources. This brown region, which is marked out space, is the region, the frequency from something like 10 microhertz to about 1 hertz is the frequency that can be observed from space. And finally, this very low frequency region, nanohertz to hundreds of nanohertz, is what can be observed with what are called pulsar timing arrays, and I'm going to discuss that in some detail as we go along. So this frequency mass diagram basically summarizes where the sources are and what are the opportunities to observe them, and what kind of properties we can observe. Yeah.
So just that last line, I didn't quite understand. So those are the quasi-normal modes? So,
These ones here.
yeah.
These are the quasi-normal modes.
So one is in spiral, and then I can picture things going faster and faster.
Yeah.
There being a frequency gap.
Yeah.
But once they merge, why should the quasi-normal mode be an upper bound on?
Because in reality there isn't. There can be any frequency, but not much energy seems to be deposited in higher order
There's
modes.
nothing in spiral, right? There's just a single black hole.
That's correct, which is oscillating and emitting
Right. So why
waves.
should we care about, why should we
Those
care about
frequencies.
what went before? It would just
Oh, it's the quasi-normal mode frequency goes like 1 by the mass of the system. That's
It's just a mass, right?
yeah. That's right. Therefore, if you have lighter masses, then you have higher frequencies, and it will be at least something. That's the 2-2 mode. The 2-2 mode for a 10 solar mass black hole is like 1.2 kilohertz, whereas 3-3 mode will be higher. The quasi-normal mode frequency is 1.2 kilohertz, but the in-spiral frequency for a 10 solar mass black hole is more like 400 hertz. So the in-spiral regime ends, and quasi-normal mode frequencies are at least a factor of 3 higher, typically. So now let's go on to look at the full spectrum of the gravitational window and what are the opportunities to observe them. This goes from all the way from the size of the universe in wavelength, right? That's really the wave frequency here, and wave period. I didn't show the wavelength. That's the age of the universe here, whereas it goes all the way to milliseconds. So we expect gravitational waves to be emitted in all these frequencies, and there are instruments in some of those frequency windows and gaps in other regions. At the highest frequencies, we expect compact objects like stellar mass objects, maybe intermediate mass black holes, hundreds of solar masses to be observed in that frequency window. At lower frequencies like microhertz to millihertz, the law stable orbit frequency and the quasi-normal modes correspond to supermassive black holes. So the masses that are observed there correspond to something like 10 to the 8 solar mass at the lowest frequencies to something like 10 to the 4 solar masses. And there we have several detectors, and I'm going to describe them. At still lower frequencies, like periods of the order of years to tens of years, this frequency band can be observed by precision timing of pulsars, and I'm going to describe what are the opportunities for observing them. On the scale of the age of the universe itself, the cosmic microwave background can carry signatures of gravitational waves that may have been created in the early universe, and that's the opportunity to observe primordial gravitational waves. So you see gaps in these regions. There may be some very interesting sources in this frequency window, but there are no instruments or abilities to observe there. There is very important gap here where there are very interesting sources, but we are trying to close the gap in this region here from 1 hertz to few tens of hertz with building some detectors, and I'm going to talk about them too. So let's start with the ultra low frequency, where the frequencies are at the level of 10 to the minus 16 to 10 to the minus 14 hertz. Planck satellite has been the recent mission which was sent to observe the cosmic microwave background, produced one of the most accurate picture of the CMB sky. But what is interesting is not what is contained in that, but rather what is contained in the polarization map, because this contains what is called the temperature anisotropies. Some regions are hot, some regions are cold, but that's not what is interesting from a gravitational wave point of view, because the map that you are seeing is probably produced only some 300,000 years after the birth of the universe. There was a Big Bang, there was inflation, and there were many interesting processes that took place in the early universe, and finally very strongly interacting photons decoupled with the rest of the matter, and we have the cosmic microwave background that contains imprint of the state of the universe when the universe was pretty old, 300,000 years. but gravitational waves that were produced decoupled from the rest of the universe very early on, and they could carry the imprint of what happened right at the birth of the universe. And what happens is this cosmic microwave background can be scattered by the gravitational waves that are traveling freely and can carry the signature of the properties of those gravitational waves. And that is shown in the next slide. Namely, what that scattering does is to cause a polarization anisotropy on the sky. And there are two kinds of anisotropies in polarization that we can have. Either we can have what are called E-mode polarization anisotropies, namely polarization patterns that have no handedness. These are left-right symmetric, and these are called E-modes, and they have been discovered. They were predicted and they have been already detected, and they have certain astrophysical information, whereas these B-mode patterns, the polarization pattern in this case has different handedness for the left-handed and right-handed ones, and these are predicted by gravitational wave scattering because it preferentially causes one of these scatterings to occur, and therefore what is predicted is this anisotropy in units of microskelvin as a function of scale on the sky. The E mode was predicted and has been detected, whereas the B mode predictions are at a level where it has not been possible to make any detections. But the problem here is that there is weak gravitational lensing by intervening matter, which could also cause B mode polarizations, and the confusion caused by those is the one, to distinguish between what is caused by gravitational waves, what is caused by weak lensing is what the challenge is. But if we are able to detect them, we might be able to have information about what went on in the early part of the universe and whether it's necessary to have extra dimensions as required by string theory. So discovering B-mode polarizations is a big deal. Whether or not that happens with Planck data, we'll have to wait for another year to see, because Planck has released temperature anisotropy maps but not polarization maps. The analysis is still ongoing. At frequencies in the region 10 to the minus 10 hertz to 10 to the minus 8 hertz, this is a very interesting band, and a band in which the first detections might actually occur. And this is done by using an array of pulsars, by timing arrival times of radio pulses, by using an array of very precisely timed millisecond pulsars. The basic effect is described schematically here. You have a gravitational wave background in which Earth is buried. You have an array of pulsars which are monitored. The pulsars, as they arrive at the Earth, will carry the signature of gravitational waves that are passing by themselves, as well as gravitational waves that are passing by the Earth. In other words, if you look at the timing of radio pulses from pulsars, you have both a component that contains gravitational waves passing by the pulsar as well as passing by the Earth. But if you have an array of pulsars, you can correlate the timing from this array, and in the correlation, the gravitational waves that are passing by will be common to all of those, and therefore you will be able to pick out gravitational wave signals passing by the Earth or in the vicinity of the Earth, and this is what is done by timing an array of millisecond pulsars. And they are sensitive to very low frequency. It's really determined by how frequently they can make observations of radio pulses. Typically they take radio data once in a day, once in a week of any given millisecond pulsars. If you observe continuously, there is really, you can have sensitivity to higher frequencies, but the sensitivity is not so good at lower frequencies. There is something called red noise, which is the reason why pulsar astronomers are targeting very low frequency gravitational waves. And there are opportunities to detect gravitational waves in this window and many observatories are timing for many, many years, up to 20 years or so in some cases. There is the Parkes Pulsar Timing Array, or PPTA, European Pulsar Timing Array, which uses several radio telescopes in Europe, and North American Nanohertz Observatory for Gravitational Waves called NanoGrav. So these three are the main international collaborations that are searching for gravitational waves in pulsar timing residuals. Very soon they are expected to combine the data to achieve better sensitivity in what is called the International Pulsar Timing Array. What are the sources that they could observe? The sources are obviously in that frequency window of 10 to the minus 9 hertz to 10 to the minus 7 hertz. Recall that 10 to the minus 9 hertz is something like 30 years. So we are talking about having very long observational period, and typically an observer in pulsar timing array might observe one wave, one single wave in their entire observational career. Okay, so that's the kind of waves that they observe, but they could be produced by coalescence of black holes that formed in the early universe and grew by coalescence. So one of the models for the way black holes at centers of galactic nuclei grow is that initially the seeds were very small, but then they accreted or coalesced with each other. They may accrete gas and grow, but they can also coalesce with each other and grow and become bigger and bigger. If this hierarchical growth of black holes at centers of galaxies is true, then the population of galaxies throughout the universe, galaxy mergers, must produce a stochastic gravitational wave background, and that's one of the prime targets for pulsar timing arrays. And this graph here shows the current state of art in what is the limit set on. No detections have been made but by pulsar timing arrays, but this shows what is the current state of the art, and this is the energy density in gravitational waves compared to the closure density of the universe. Let's recall that the matter energy density fluctuation is at the level of 10 to the minus 5, whereas for gravitational waves, pulsar timing arrays in this frequency window of 10 to the minus 9 to 10 to the minus, well, few times 10 to the minus 9 to 10 to the minus 7 hertz have set the upper limit of few times 10 to the minus 8. The latest results are actually about a factor of 5 better, few times 10 to the minus 9. Latest results really push down that. There are many other upper limits that have been set. I won't talk about them here, including the one by LIGO 5th science run, but that's at a much higher level than the pulsar upper limit, although it's in a different frequency window. So there are many constraints on stochastic gravitational wave backgrounds, but this can improve by 2 or 3 factors of 2 or 3 very quickly, where potential discoveries are expected. That could be in the period of next 4 to 5 years. So we are very much expecting pulsar timing arrays to make detection soon of stochastic gravitational wave backgrounds from supermassive black holes. But in the future, things like square kilometer array, which are currently being planned, can push that sensitivity to even further. So that's the state of the art in this field. Yeah.
So this is the stochastic background produced by the sort of early universe.
It could be anything in principle,
But
but
you don't have any background, for example, from supermassive black holes in this plot.
why not?
So in this one, we don't have any. I was wondering if you were to draw a line of the supermassive black hole.
Oh, where would they lie?
They lie.
No, it is expected somewhere here as well. You mean what is the how it goes?
It
How
has
the-
power laws. It is like a red noise.
Yeah, it is a power line. Omega, I think it goes down like that.
Yeah.
Okay, it goes like f to the I don't remember what's the
It's some negative power.
yes,
So
it's a
how
power
close
line.
is this to the expected values of this power
For
amplitude?
supermassive black holes,
Yeah.
for supermassive black holes, it's a factor of 4 away from some models. I removed a slide that I had included, but it's about a factor of 4 away from predicted supermassive black hole background. Yeah, I better hurry up because quite a bit to cover. At low frequencies, which is the frequency window from something like 10 to the minus 5 hertz to 10 to the minus 1 or even 1 hertz is what we call low frequency, and there we cannot detect waves from space. We have to, from ground, we have to go to space. That's the best project that is, the project that has been best studied, not necessarily the best project. The project best studied is what is called the Laser Interferometer Space Antenna. The latest in this is called not LISA but ELISA, which is Evolved LISA. It consists of 3 spacecraft in heliocentric orbit as shown here, with spacecraft 1 million kilometer apart and at an inclination of 60 degrees to the ecliptic, and the orbital configuration is such that it produces a cartwheel as the 3 spacecraft orbit the sun, and that's entirely due to celestial mechanics. There's no need to have any rockets making them go in and out of the ecliptic. It's entirely due to celestial mechanics. This triangle rotates like a cartwheel as the craft orbit, and that's very important because it causes additional modulation in the signal, which helps us to extract more signs. Very recently we submitted this as a white paper to the European Space Agency, and the outcome of that will be known somewhere in October or so. So this is one of the missions that is going to make for sure discoveries, because just as explained before, when you have a population of black holes merging and producing stochastic backgrounds, obviously some of them will be foreground galaxy mergers that you could observe, and this particular simulation shows how within a Hubble time, you can see the time here, which is 2.6 gigayear, 3 gigayear, 4.8, 5.1 and 5.122, and the merger has taken place pretty much within the Hubble time, starting from typical galaxy separations. So these mergers occur pretty frequently, like once in a year, maybe a few times per year, and they can be observed in ELISA. This slide shows how bright these sources will be in ELISA as a function of redshift and log of the mass. Therefore, this is 10 to the 5, 10 to the 6, 10 to the 7 solar masses. These are the typical masses that ELISA might observe. And look at how big is the range of ELISA. It can see emerges all the way up to 20 with pretty big signal to noise ratios of something like 50, which means we can not only observe these sources, but also we can learn quite a lot of astrophysics from them. You know, what is the rate at which black holes grow in the universe, what was the mass function of black holes, and so on and so forth. So there's very big science. Not only can we observe them, but we can also make very accurate measurement. I won't spend any time on this, but this slide shows how we can measure masses and spins pretty accurately for sources even at z equal to 1 and z equal to 4. But not only can we observe coalescence of supermassive black holes, but we also know from observations of the center of our own galaxy, where there are stars orbiting Sagittarius A, which is supposed to be the location of our Milky Way galaxy, about 4.5 million solar mass black hole. So there are stars going around. That's not what we are interested. These could produce tidal disruptions and extremely bright electromagnetic events, which astronomers are now already beginning to observe. But when compact objects like that fall in, they will produce gravitational waves which carry the signature of the curvature of space-time around black holes. The next slide goes on to show that. Namely, when small black holes fall into big black holes, as in the previous slide, they produce very complicated orbits, as shown in that animation, with signals carrying structure of the space-time around the big black hole. And studying them can tell you about the Kerr geometry, but also test general relativity in strong field regime. The last and the final frequency region of interest to us is the high frequency one, which is where most of the activity is currently taking place. And there are many detectors that are built and operated. These are ground-based gravitational wave detectors. There are two locations in the US where the interferometric gravitational waves are built. One is in Hanford in Washington State, and one in Livingston in Louisiana State. These two have taken data together with the Virgo, which is in Italy, in Pisa. These are 4-kilometer arm length detectors. Virgo is a 3-kilometer arm length detector. GEO is a smaller detector which is used for constructing new technology and testing it, but also it is in astro watch mode when the bigger detectors are not taking data. And that's true currently. Currently, none of these bigger detectors are operating. They are in a upgrade mode where we are replacing mirrors and suspension systems to make them more sensitive, but we don't want to miss a supernova or some other merger event that might take place close enough. So while these bigger detectors are being upgraded, GEO is watching, taking data and watching the sky. In addition to these, there is also a funding available to build a detector in Japan. It's called the Kagra detector, and that will be the first underground detector, and they are going underground for reasons that I'll mention in a minute. In addition to these, which are already funded, we are awaiting decision by the Indian government to build a detector in India, and that is with contribution of instrumentation from the second detector which existed at the Hanford site. And if that comes through, then we will have a fantastic baseline to observe gravitational waves, as I will talk about in a minute. So I had not remembered that I had put those slides. So those are the various detectors. No detections have been made in spite of something like 2 years worth of data taking and analysis. Nothing has been detected so far, and you will see some of the astrophysical results in Sukanta Bose-Stark. What are the upper limits that have been set, and when do we expect to make detections will be discussed in Sukanta Stark in a couple of days, or maybe next week or so. Yeah. So what is the schedule? What do we expect to have over the next 5 to 10 years? By 2015, just a couple of years, we expect the two US detectors to operate, and their baseline is about 10 milliseconds. Baseline is a big deal in this field because we cannot really see where the sources are. The bigger the baseline, the better is our sensitivity to localizing sources. And Bala Iyer in his talk is going to talk about how locating one of the Hanford detectors to India is going to make a big difference. By 2016, we expect Virgo to operate. That will give us 3 detectors, which is the minimum that is required to localize sources on the sky. Another couple of years later, we expect the Japanese Kagra detector to operate, and that will further increase the baseline. But all these detectors are in the northern hemisphere, and they don't really do a good job of making distinctions between different polarizations. And to have a detector in the southern hemisphere or close to the equator gives you a very big volume, and that is very, very important. It not only increases the baseline, but it gives us a configuration wherein we can do polarization measurements far better, and that's the importance of having LIGO India. How well can gravitational wave detectors see the sky? This slide shows what is called the antenna pattern of gravitational wave detectors. If it is red, that means it has good antenna, good sensitivity in that direction. If it is blue or black, that means there is no sensitivity. So this is the Malveed plot where the vertical axis is simply the co-latitude, and this is the azimuth angle. The Hanford detector is located somewhere there on the sky, on the Earth, and its sensitivity to sources on the sky is shown here. It has best sensitivity of about 1. That's in just overhead, so you have Hanford detector like this, any source that is coming perpendicular to the plane of the detector, it will have the best sensitivity, but also in the opposite direction. So those are the two best spots for its detection. But it has blind spots in the plane of that, and or the two arms. If you have sources in the plane of the arm or in the opposite direction, you have absolutely no sensitivity, and those are those blind spots. If you look at the 3D plot of this is nothing but the quadrupole pattern. So there are some sources, directions to which the detection sensitivity is very good, other directions it is not so good. If you add the LIGO Livingston detector, then some of the blind spots go away because its orientation is similar, but it's in a different location. Therefore, some of the blind spots go away, but there is still considerable gap in the sky where we can't observe the detectors, sources. So if we include more detectors, such as the Virgo, even better sky coverage, but with something like 5 detectors, we can watch the entire sky and in the entire frequency band. That means a network of detectors of gravitational waves is always on and sensitive to quite a variety of sources, signals that last for milliseconds or up to years. Multiple signals could be in band, and therefore the challenge is to dig out these signals, and to be able to do so, we use match filtering. And this is the reason why this school, which was held last week and last couple of weeks, right, and the workshop that's going on for 2 more weeks is going to address the question of how accurate do we need to be to dig out signals. So that's the challenge, but are we confident in our data analysis pipelines? Have we met those challenges? Can we really detect gravitational waves? We did have a gravitational wave event in the latest data that we took 3 years ago, October 2010. We had a run that completed in towards the end of October. Within a day of taking the data, we could see a signal. Within several months, we completed all the analysis and we wrote a paper, and we were about to publish this event. And let me explain what's going on here. This shows you cumulative rate of events that come out of our detector as a function of the signal to noise ratio threshold that we put in. So if we use very low threshold, of course we will see loads and loads of events. They could be from instrumental origin, or it could be due to environmental factors or whatever, or it could be gravitational waves. It could be anything. So we have to somehow get a handle on measuring the background rate of gravitational wave events. This background is computed by time shifting events from one detector related to another and then comparing what the coincidence events are. If you had no time shift and if you compared the events, they could be true gravitational wave events. If you time shifted the data and then look for coincidence in different gravitational wave detectors, they're obviously false alarms. So this time shifted data gives you that background, and on top of that you have these blue triangles which gives you a measure of what is the zero lag event or no time shifts. Those could be true gravitational events, but there's no way of telling. So what we do is to plot them on a graph like this, and we ask what is the chance that any one of these triangles is due to purely instrumental noise or due to environmental noise. Well, for all these events you can say there's a pretty good chance it is just caused by instrumental noise. Whereas this one event here which stands out, and what is the chance that our instrument can mimic it? It's about 1 in 7,000 years. So if you took data for 7,000 years, there's a chance that one event of those backgrounds might be appearing there. But we took data for only about a couple of years in all of LIGO, so this is an extremely significant event. So we were about to publish this result, but it turns out this is what is called an injection, that is an artificial simulated signal put into the data, which is done secretly in order to test our pipelines. So when we discovered that, of course, we were happy that we were able to detect it, but we were unhappy. It's not a true event. It is something that's put by experimentalists to test us, which of course we knew. It's not as if it's done entirely secretly, but that was a very good exercise. Now, this noise in the detectors look like this. This is the noise power spectral density as a function of frequency. This shows how what we did during the so-called the 6 science run, and over the next few years from 2015 to something like 2018, we expect the sensitivity evolution to take place, and we know that we can achieve it because if you look back how this sensitivity was achieved, that was from something like 2002 to 2007. So I think we can get there from, this will be advanced LIGO when it begins to operate in 2015. Over 5 years, I'm sure we will be reaching this blue curve or even this black curve. So that's the sensitivity evolution, and what can we expect with those kind of sensitivities over the years is plotted in this. It's a busy plot. The same thing is true for Virgo. It will come online by 2016, but what can we expect? That's highlighted in this shaded area. By about 2016 or 17, we expect to detect anywhere between 0.006 events per year, that means almost 1 in 100 years, to about 20 per year. That's the uncertainty in the rate of events that we expect. But the median rate there in this region is about a few events per year, 1, maybe 2 events per year. That's what we expect, and that's the reason why the time scale to look for the big announcements is really 2016 to 2018. Now, to do astronomy, we need to localize sources in a small area on the sky, and that we cannot do with this network, which consists of only LIGO and Virgo. Other detectors will come online, and they can then increase the number of sources which we can localize to much greater degree, and that will be the subject of Bala Iyer's talk. For details, please see this article. I'm going to put this talk on the web. Sources in advanced detectors, there are many different things that we can detect. I'm not going to talk about that. There are other people who are going to discuss that. I will end by just talking about what after advanced detectors. One of the big problems with ground-based detectors is that if you look at all these different frequency evolution, the sensitivity evolution from 2015 to 2020, you see that, but there are very, very interesting sources down there, and to go there, the sensitivity, either you have to go to space, which is what LISA does, or you have to go underground. And one of the concepts that is being studied in Europe is called Einstein telescope. To go underground by something like 200 meters up to a kilometers, you can then isolate man-made sources. They're all up there. Also, some of the noise, gravity gradient noise sources caused by density variations on the surface of the Earth, etc. So going underground has a real advantage. Not only that, the Einstein telescope is considering building a detector, building 3 pairs of detectors, utilizing each of the arms of the triangle twice. You can have like this, 3 different V's. And these 3 detectors enable us to construct what is called the null stream. Without going into technicalities, a single gravitational wave detectors cannot really be shut off from the sky. No matter what you do, you'll be sensitive to gravitational waves. But if you have 3 detectors, like in this particular case, aligned in this way, then you can completely shut off. You can construct a stream which is completely devoid of gravitational waves coming from anywhere in the sky. And that's a great advantage, because I told you the difficulty is we don't know how to measure background noise, and ET will completely avoid that. And it will be able to tell us what's the gravity gradient noise, what's the gravity gradient on other noises that we have to put up with. So with ET, we will increase both the frequency and strain sensitivity, and that will give us many new sources in this low frequency window. Let me stop there, and thank you again for giving me the opportunity to tell you something about what's going on over the next 10 to 15 years. Thank you.
Thanks a lot, Sophia, for this exciting overview.
Yeah.
Sagittarius.
Yeah.
Sagittarius star.
Yeah.
I'm just wondering, in one hand, as you said, that small black hole, stellar mass black hole is interacting with, merging with supermassive black hole and gives rise to the
Yes.
accretion radiation.
Yes.
But in this case, suppose I'm talking about the accretion disk around Sagittarius A star.
Yeah.
Small black holes are also interacting
With-
among each other. So, I mean, from practical point of view, is it easy to? I understand theoretically, big black hole is merging with small one and small. They are having different wavelengths.
Yes.
But how, in practical sense,
How can you separate?
separate?
Okay, okay. This is something that we have already looked at both in the case of LISA as well as Einstein telescope. If there are multiple sources, so one of the challenges is gravitational wave detectors are sensitive to almost the entire sky, to many different frequencies. But it turns out that we have very good discrimination between different template waveforms. In fact, if we take waveform from 1.4 binary black hole and compare it with 1.5, they're vastly different. So by using this match filtering, we can dig out signals pretty well. But eventually they may cause a confusion background, a background beyond which we can't detect anything. And it turns out that yes, in advanced LIGO, potentially there may be a background gravitational waves caused by a population of these sources, but while we can detect them, they are not going to be worse than the instrumental noise. I showed you sensitivity curves. They will not be above that. In the case of LISA, actually, white dwarfs in our own galaxy was much worse than the instrumental noise itself. So there was no point in making instrument better. But in advanced LIGO, that's not going to be the case. That's our expectation. We don't expect binaries in the universe to cause a confusion background. We will see all the foreground sources, in fact.
With the Einstein telescope, so two of those detectors be used to do cross correlation to measure stochastic gravitational background?
It depends on how well we can trust, let's say, making estimates of local disturbances. H1, H2 had similar problem. So, whereas in Einstein telescope case, we can construct the null stream. We can take the null stream and we can subtract the true stream from that, the strain data from that, and what remains is the residue, and that will contain true gravitational wave signatures. And in this way, in Einstein telescope Mark data challenge, we did two things. One is to cross-correlate data from two different detectors, but also look at the residue, and we could detect stochastic background by both methods, and they are consistent. Okay.
So the bound on omega can actually be better than, say...
It's about 10 to the minus 11. You can go up to 10 to the minus 11 with Einstein telescope. Probably a few factors of a few better, but that's the level at which we expect.
But still, it's much above the understanding.
Absolutely, yeah. There could be phase transition. It's much above, inflation, but not, there are other sources which could be there. Mostly the population of binaries, that could be very important there.
Okay. So,
Thank you. Oh, sorry. What is this part?